rising high above the Atlantic Ocean, dominating the skyline of Tenerife, stands one of Europe's most iconic natural landmarks, Mount Teide. At 3,715 meters, it is the highest peak in Spain and the crown jewel of the Canary Islands. To millions of visitors each year, Teide appears calm, majestic, even timeless. But beneath this stillness lies a system that is anything but dormant. In recent years, scientists have detected unusual signals, swarms of earthquakes, subtle ground deformation, and shifts in volcanic gases, all pointing to one unsettling possibility. The system beneath Teide may be waking up, and that's what makes this volcano so dangerous. It looks quiet, it feels stable, but deep underground pressure is building. Rising from the heart of Tenerife in Spain's Canary Islands, Mount Teide dominates the Atlantic horizon as one of the most striking volcanic landscapes on Earth. Located off the northwest coast of Africa, the Canary Islands are not part of a tectonic plate boundary, but instead sit above a powerful mantle hotspot, an upwelling of molten material rising from deep within the Earth. Teide is the highest peak in Spain and the third largest volcanic structure in the world when measured from its base on the ocean floor. But the mountain we see today is only part of a much larger system. Teide sits inside the vast Las Cañadas caldera, a massive volcanic depression roughly 16 kilometers across. This caldera was not formed gradually. It was created by a catastrophic event. Long before Teide existed in its current form, a much larger volcanic system occupied this region. Over time, repeated eruptions emptied enormous magma chambers beneath the surface. As these chambers drained, the ground above lost its support. Eventually, it collapsed inward, forming the enormous basin that now defines the heart of Tenerife. Teide rose later within this collapsed structure. Layer by layer, eruptions built the stratovolcano upward, creating the towering peak seen today. But this history reveals something crucial. Teide is not an isolated volcano. It is the latest expression of a much larger system that has already demonstrated its ability to produce large-scale collapse and powerful eruptions. The caldera is not just a geological feature. It is evidence of what this system is capable of. Before we continue, don't forget to click on that subscribe button and like this video, as it's the best way to support this channel. Deep beneath Tenerife lies the true source of Teide's activity, a steady supply of magma rising from a mantle hotspot. Unlike volcanoes found along tectonic plate boundaries, the Canary Islands are formed above a plume of hot material rising from deep within the Earth's mantle. This plume continuously feeds magma into the crust, where it collects in reservoirs at different depths. Studies suggest that Tenerife's volcanic system contains multiple levels of magma storage, ranging from deep reservoirs more than 20 kilometers below the surface to shallower pockets closer to the volcano. This layered structure is critical. It allows magma to move upward in stages, sometimes pausing for long periods before continuing its ascent. It also means the system can remain active even during long, quiet phases without visible eruptions. Recent geophysical data indicates that these reservoirs are not static. Magma appears to be shifting, accumulating, and pressurizing parts of the system. While this does not guarantee an eruption, it confirms that Teide remains connected to a living and evolving source of energy beneath the island. Although Teide appears quiet today, its geological past tells a far more dynamic story. The most recent eruption on Tenerife occurred in 1909 at Chiñero, a vent on the island's northwest flank. This eruption produced lava flows but was relatively mild compared to more explosive volcanic events. Earlier eruptions in the 18th century caused greater disruption, damaging infrastructure, and reshaping parts of the coastline. These eruptions were still primarily effusive, meaning they involved flowing lava rather than violent explosions. However, further back in time, Tenerife experienced more explosive activity. Geological evidence shows that the island has produced eruptions capable of generating ash clouds, pyroclastic flows, and widespread disruption. These events were driven by changes in magma composition, gas content, and pressure within the system. This dual behavior, generally gentle eruptions punctuated by occasional explosive events, is what makes Teide particularly complex. It is not a volcano that behaves in a single, predictable way. Over the past decade, scientists monitoring Tenerife have observed a noticeable increase in seismic activity beneath the island. These are not large, destructive earthquakes, but clusters of small tremors known as seismic swarms. One of the most striking episodes involved more than 1,000 micro-earthquakes occurring within a single day. Individually, these tremors were extremely weak. Collectively, they revealed something far more significant: movement within the volcanic system. Most of these earthquakes occur at depths between 10 and 30 kilometers. This places them within or near the deeper magma reservoirs beneath Tenerife. The leading explanation is that magma, or volcanic gases, are shifting, fracturing surrounding rock as they move. What makes these swarms especially important is their pattern. They are not random. They occur in concentrated bursts, often clustered in specific regions beneath the island. This type of activity is widely recognized as a key indicator of volcanic unrest. The persistence of this activity indicates that the system is active and evolving beneath the surface. The key question is whether this unrest could eventually lead to an eruption, and what that eruption might look like. The most likely scenario is a relatively small eruption from one of Tenerife's rift zones. These eruptions typically involve lava emerging from fissures or vents on the flanks of the island. While they can cause local damage, they are usually limited in scale and impact. However, there is a second possibility that cannot be ignored: an explosive eruption. Explosive eruptions occur when gas-rich magma rises rapidly and pressure builds faster than it can be released. This can result in violent fragmentation of magma, producing ash clouds, pyroclastic flows, and widespread disruption. Teide has produced explosive eruptions in the distant past. If conditions within the magma system were to change, particularly if more viscous, gas-rich magma accumulates, the risk of such an event would increase. In the extreme case of a massive eruption or caldera collapse, there is a potential for triggering tsunamis, particularly if significant portions of the volcanic structure collapse into the ocean. Such an event could generate waves that threaten not only Tenerife, but also nearby islands and even coastal regions of Africa and Europe. While such scenarios are rare, they are not unprecedented and warrant careful monitoring. Tenerife is home to nearly 1 million residents and attracts millions of visitors each year. This makes even moderate volcanic activity a serious concern. A flank eruption could damage roads, infrastructure, and local communities. Lava flows, though often slow-moving, can still destroy everything in their path. Ash emissions could impact air quality and disrupt flights, particularly given the island's importance as a tourist destination. A larger explosive eruption would have far greater consequences. Ash clouds could spread across the region, affecting air travel over large parts of Europe and Africa. Pyroclastic flows, if they occurred, would pose a direct threat to areas near the volcano. There would also be economic impacts. Tourism could decline rapidly, and disruptions to transportation could isolate parts of the island. One of the most important factors in assessing Teide's risk is the level of monitoring in place. Spain's National Geographic Institute operates an extensive network of instruments across the Canary Islands. These systems track earthquakes, ground movement, and gas emissions in real time. Even the smallest changes can be detected and analyzed. This provides a critical advantage. Volcanoes rarely erupt without warning. Changes in seismic activity, deformation, and gas emissions typically occur before an eruption. With modern monitoring systems, these warning signs can be identified early. The challenge is not detecting change, it is interpreting what those changes mean and determining whether they signal a progression toward eruption. Teide exists in a state that volcanologists often describe as restless. It is not erupting, but it is not inactive. It is a living system, continuously shaped by forces deep beneath the Earth's surface. The recent earthquake swarms, including episodes involving more than 1,000 tremors in a single day, are clear evidence of this ongoing activity. They are not signs of immediate danger, but they are reminders that the system is evolving. For now, the volcano remains stable. The magma is deep. The signals are subtle. Life on Tenerife continues without disruption, but the story of Teide is far from finished. At some point, whether years, decades, or centuries from now, the pressure beneath the island will be released. When that happens, the nature of the eruption will depend on conditions that are still developing far below the surface. And that is what makes Teide so fascinating. It is not just a relic of past eruptions. It is a volcano with a future, one that is slowly, quietly, and invisibly taking shape beneath the island today.